Yeah, let's actually get started. Good morning, everyone. Welcome to our PKU Math School Colloquium series. This week we are very honored to have Professor Peter Carr from NYU joining us. Professor Carr's talk today is titled
Recording in progress.
Optionality as a binary operation. Just a quick reminder that this talk will be recorded and shared online afterwards. Please keep yourself muted if you're not speaking. I'll begin with a brief introduction of Professor Carr. Although everybody knows you and you probably don't really need an introduction. Dr. Peter Carr is the chair of the Finance and Risk Engineering Department at the NYU Tandon School of Engineering. Prior to his current post as full professor, he headed various quant groups in the financial industry for 20 years. He also presently served on the board of the National Museum of Mathematics, World Quant University, and two startups called MoneyStatNav and Life Navigator. So prior to joining the financial industry, Dr. Carr was a finance professor for 8 years at Cornell University after obtaining his PhD from UCLA in 1989. He has over 100 publications in academic and industry-oriented journals and serves as an associate editor for 8 journals related to mathematical finance. So Professor Carr is widely cited. Google Scholar currently ranks him 3rd in the world in quantitative finance, 2nd in derivatives, and 1st in volatility. He was selected as Quant of the Year by Risk Magazine in 2003 and Financial Engineer of the Year by IQF Sungard in 2010. So from 2011 to 2014, Dr. Carr was included in Institutional Investors Tech 50, an annual listing of the 50 most influential people in financial technology. So finally, on a personal note, I actually had the honor to meet Professor Carr in person before the pandemic. And I know that despite his impressive suite of achievements, Professor Carr is also incredibly supportive to young scholars, myself included, as well as students, including many of our own students here and across China, who went on to pursue more education in the program that Professor Carr runs. So thank you very much, Professor Carr. It's really our great honor to have you here today, and the floor is all yours.
Well, thank you, Rickson. It was a perfect segue where you mentioned more education because it turns out I'm the chair of the department that offers a master's degree in financial engineering in New York. And of course, we would welcome applicants from PKU, and I'm sure we would very seriously consider every such application. So, okay, so with that, let me share a screen. And so the title, as Rickson said, is Optionality as a Binary Operation. And you can see I decided to play a little game with words. So obviously the word option is an optionality, but it's also in the operation part of binary operation. And so we'll be drawing a natural connection between these two different phrases or words from two different fields. So let's start with math. So the question is, what exactly is a binary operation that those mathematicians talk about? And so in math, a binary operation is a calculation that combines two elements called operands from the same set to produce another element in that set. So familiar examples are addition over reals, multiplication over non-negative reals, subtraction over reals, and division over reals. And I actually, in the process of doing this work on applying algebra to finance, realized something about really basic arithmetic that I never actually had realized, even though I've worked with these symbols my whole life. So look at plus and look at times, and you see that you do a rotation of the plus by 45 degrees to get the times, okay? Now look at minus and compare it to the plus above, and you see that all you do is remove the vertical bar. Now look at division and compare it to the times above, and you see that all you do is remove a horizontal bar. And moreover, the way you get division from subtraction is by a 45-degree rotation. Isn't that amazing? I mean, I don't know if you ever picked that up, but I feel like that's just, too cool. All right, anyway, so there are other binary operations besides those four very familiar ones. So, for example, Albert Einstein, who needs no introduction, had in his special relativity introduced a velocity addition formula, it's called, and the way it's applied is as follows. So let's just do a little thought experiment. So imagine that a train, a high-speed train like in China, is traveling really fast. Let's say 2/3 the speed of light, which is super, super fast. And according to an observer who's like just on the ground watching the train go by. And imagine that on the train, if someone fires up a bullet in the same direction as the train, and just for the sake of this little thought experiment, say that if you're the man who fires the bullet on the train observes the speed of the bullet, it's 2/3 the speed of light. Okay, so now imagine you're on the ground seeing the train go by at 2/3 the speed of light, and the train has windows, and you look in the window and you see the bullet, which according to the man on the train who fired the gun is 2/3 the speed of light. So the question is, what's the speed of the bullet for the observer on the ground? And so if you were Isaac Newton, you would have answered 4/3 the speed of light. And so you would have done a straight add of the two velocities. So it turns out that nothing can move faster than the speed of light. So the way you combine these two velocities is not a straight addition, even though the train and the bullet are moving in the exact same direction. So there is a way to do the calculation, and you'll end up with something less than the speed of light when you combine these two velocities. And so that's called Einstein's velocity addition formula. So the point is that an unusual binary operation is not just, let's say, a mathematical idea. It actually describes physical reality. Okay, so perhaps they could also be used to describe financial reality. And in fact, non-standard binary operations do describe financial reality. So that would be the main point of my talk, but let me do a more familiar example. It's much more immediate. So say that, yeah, go ahead. Is there a question or comment? Okay. Say that you want to invest in an American stock while you're over in China. And let's say it's American Airlines, easy to remember. So let's say that you were here in the US and you were to do a buy and hold of American Airlines. And let's say that the volatility you experience is 40%. So, okay, that's if you're in the US, if you do a buy and hold. But you're actually in China. So let's say what you would have to do as a Chinese investor is convert your yuan to dollars and then invest in American Airlines. Then after you hold American Airlines for some time, you'll sell it. And you'll take the random value of American Airlines in dollars and convert it to yuan at the random exchange rate. So let's say that the random exchange rate is 30% volatility. And and let's also say that there's no correlation between American Airlines returns and the exchange rate changes. So the question is, how much volatility does one experience as a Chinese investor when investing overseas in some foreign stock with 40% vol when the exchange rate is 30%? So if you answer 70%, you're wrong. The actual calculation will turn out to be 50%. And let's say the way you do it is you convert the two vols of 0.4 and 0.3 to variances of 0.16 and 0.09. You add those two variances to get 0.25, and then you take the square root. So you can actually think of 0.5 as a funny addition of 0.3 and 0.4 that does arise in finance. Okay, so binary operations can have various properties. So for example, ordinary addition, ordinary multiplication are both commutative, so order does not matter. Whereas ordinary subtraction and ordinary division are not commutative, order does matter. so binary operations may or may not be associative. So associative basically involves combining three things. And but since you only have a binary operation, you can only combine them pairwise. And so the sort of question is, when you combine pairwise twice in order to combine three things, does the order, the two possible orders matter? If not, then it's called associative. Okay. The set over which a binary operation is conducted may or may not contain a so-called neutral element for that binary operation. So a neutral element is an element in the set, if it's there, that when combined with every other element in the set, just leaves that other element. So the set that we're doing binary operations in may or may not contain an inverse element for the binary operation. So formally, having already defined a neutral element, if there is a neutral element, then there may or may not be an inverse element. And an inverse element is such that when you combine an element with this inverse element, you get the neutral element. So, okay, so we're going to illustrate these properties for a particular binary operation that we've not yet encountered on the next slide. So the binary operation I want to now focus on is the maximum of two elements. That is a binary operation. Let's say we consider the set of non-negative reals, then the point is that the maximum of two reals is real, so that makes it a binary operation. And, over non-negative reals, the maximum of two non-negative reals is a non-negative real, makes it a binary operation over that set. And this binary operation is commutative, so order does not matter, associative, so when you're pairwise combining twice, order that you pairwise combine does not matter. Has a neutral element, which is zero. So zero max any non-negative real is that non-negative real. And moreover, but there's no inverse for the max operation over the set of non-negative reals. So, for example, three max, if there were, so three is a non-negative real. And if there were an inverse in the set of non-negative reals, then it would have the property that 3 maxed that inverse element gave us 0. But you won't find any number that you can max with 3 to give you 0. It doesn't exist. Okay, so the other thing is when you think about 2 or more binary operations with one of them being maxed, then the second binary operation will distribute over max as long as it's an increasing binary operation. So by increasing binary operation, examples would be ordinary addition. So, let's say over non-negative reals, you add 2 non-negative reals, you get a bigger number. Ordinary multiplication, you multiply 2 non-negative reals, you get a bigger number. So addition and multiplication over non-negative reals is an increasing binary operation, and they both distribute over the max. Even, let's say another binary operation that's increasing is raising a non-negative real to another non-negative real. You get a non-negative real, and even that raising operation distributes over max. So, okay, so so in particular, ordinary multiplication distributes over max over the set of non-negative reals, and of course, you were taught in probably 3rd grade that ordinary multiplication also distributes over ordinary addition. So the question now becomes, does ordinary multiplication distribute over other binary operations besides, say, plus and max? And so it does, is the quick answer. It would distribute over the min, for example. A different question is that plus and max are both associative, so does ordinary multiplication distribute over other associative binary operations? Well, min is associative, so the answer is yes. And but we'll be thinking about yet other binary operations that are associative, for which ordinary multiplication does distribute over. Okay, so in math, there's this notion of algebraic structure, and it consists of a non-empty set. We'll call it A, because I'm Canadian and we say A a lot. There'll be a collection of one or more binary operations defined on A. and a finite set of identities known as axioms that these operations must satisfy. So we're going to be interested in this talk in algebraic structures with exactly one binary operation. So there's actually terminology that mathematicians made up for such algebraic structures. So a magma is a algebraic structure with exactly one binary operation, and one requires for a magma that the binary operation be, be commutative, actually you don't, sorry, I take it back, what commutative. So it needs to be, I have to check, I think it's associative. Okay, and associative. And then if it's unital, it means there's also a neutral element. And okay, and just a minute. No, I take it back about magma, sorry. All you need is closure, and that's it. So not much structure. And then if it's unital, then there is a neutral element. And then if it's also associative, then it's called a monoid. So then there's algebraic structures with exactly two binary operations. So a ringoid is a algebraic structure where the two binary operations are both closed, and moreover, the second binary operation distributes over the first. Semifields obviously have two binary operations, and they must both be associative as well. And they also have neutral elements, both binary operations, and the second distributes over the first. Okay, and finally, the second binary operation has an inverse, but the first does not. Okay, so anyway, so there's all these technical names for different kinds of algebraic structures. And let's say, you know, people only study structures which have applications typically. And so, you know, both of these structures that we just saw have applications. So you can have algebraic structures with three binary operations. So say times, plus, and max. And you know, what's kind of interesting about this one is that times distributes over plus, and plus distributes over max. And I actually gave a talk earlier today where this was used. And okay, so far we've been doing math and talking about binary operations and the algebraic structures involving them. But on the other side, we have finance and this term called optionality. So what exactly is this optionality? And so it's a term that describes the contractual ability of a security holder to choose between two or more alternatives. And we'll first consider optionality when there's exactly two alternatives in order to relate optionality to a binary operation, which combines two numbers. So one of the alternatives will always be a riskless amount, while the other will actually be a risky amount, so have positive variance. And on the next slide, we're going to introduce a new financial contract that I've been calling a stoption, which will contain several of these binary choices in the contract. So and also, like, there'll be special cases of stoption that reduce to familiar contracts, such as a zero coupon bond and a convertible bond. So let me tell you about this financial contract that I call stoption. So first, disclaimer, does not yet trade, although special cases of it do. And but it turns out to be a fairly natural contract when you're thinking about the interaction of abstract algebra and derivatives. And it's a path-dependent financial security. And moreover, it has like Bermudan exercise style. And so it's a, you know, fairly complicated financial security, and yet you'll see we'll be able to like value it in closed form in both familiar models and less familiar models. So, okay, so let's just recall, to motivate it, let's just recall that a static $1 investment in the stock market for n periods subjects the investor to n daily gross returns. And the gross returns are price ratios if there's no dividends. So which we'll assume. And we're also going to be assuming that the stock price is never zero. So because to calculate a gross return, we look at a price ratio and we don't ever want to divide by zero. So, okay, so, let's say the trouble with just doing an investment in the stock market is that one of those gross returns might be very, small, like let's say 1/10. Okay, and if it was 1/10, that means you lose 90% of your wealth when that happens. And that's a bad thing. So wouldn't it be nice to have some kind of protection against gross returns that are below 1, and by definition, they have to be above 0. So gross returns like 1/10. And so the stoption is a way of granting protection to somebody who's just doing a buy and hold. And because it embeds a Bermudan style exercise feature into this investment. So the way a stoption works is that you can exercise it on any one of n days. And if you do exercise on some day, let's say J, then you're going to receive a cash payout, which is the product of all the previous gross returns previous to this day J times a contractually specified gross return, little g, that is written into the contract and is known at time 0. Okay, so let's say let's say that for the day you exercised, the gross return on that day was 1/10, which is pretty lousy. And let's say that it so happens that for that day that you're exercising, the contractually specified gross return is, say, 1. Okay, so, or even let's make it 1.1. So instead of losing 90% if the contractually specified gross return was 1.1, you would actually earn 10%, okay, on your investment so far, that day. So obviously that's a nice thing. And so that's sort of how it works, that you can replace any gross return just after realizing it with a number that's in the term sheet. The number in the term sheet can depend on the day you're exercising. So it's being denoted by little g here, and it's subscripted by j because it can depend on the day you're exercising. And so, if you had to describe it to one of your grandparents, so not so much math, you'd say that if the stoption is exercised on some given day, then you're replacing the last gross return, which is random ex ante, by a guaranteed gross return that's in the term sheet. Okay, so that's how it works. And the reason I'm calling it a stoption is you can choose which day to exercise. You actually have to exercise once. So you could say, well, why is it an option if you have to exercise? And so again, one answer is that you choose when. And then a second answer is that actually if you just think of the underlying as the first n-1 gross returns rather than n gross returns, then if you set the final floor to 1, that turns out to describe a contract on n-1 gross returns, which need not be exercised. And so it really is an option. Okay, so it'll be easier to think about that it's written on n gross returns rather than n-1, and that it has to be exercised once. So we'll take that view, but keep in mind that you can always have this alternative view where it really is an option in that need not be exercised at all. Okay, so anyway, we're going to assume 0 interest rates and dividends. We're going to assume no arbitrage. Q here will be the risk neutral measure that therefore exists. So a guy named Steve Ross, who was at Rickson's alma mater, MIT, developed a fundamental theorem called fundamental theorem of asset pricing. It was actually named by a student, Phil Dybvig. And the statement says, if there's no arbitrage, there exists a risk neutral measure. And so we're going to call it Q. We're not requiring this measure to be unique just yet. So so there's a probabilistic representation of stoption premium, and we'll denote the stoption premium by V for value. And it's subscripted at the time we're interested in the value. And the superscript in brackets is the number of exercise opportunities it has. And if you're careful, you might have noticed I just switched from a capital N to little n. So I actually meant little n previously, and I see that one capital N has survived. So all these capital N's should be little n's. So, oh no, no, sorry, I take that back. Okay, capital N here is a random stopping time that is in the set 1 to little n. And so I actually want a capital N there. And it's a random variable that takes values on the positive integers up to little n. So, okay, so little n is sort of like written in the term sheet. It's the number of periods this stoption lasts. And the longest number of periods it can last. So, you could have a 10-day stoption, and then you could exercise once, and you have 10 different days at which you could exercise. So, we could have a 1-day stoption, and then recall you have to exercise, and so then you basically have to exchange the first period gross return for the one for G1. So you're getting G1. And so G1 is the number of the term sheet. So this is a bond. It's a zero coupon bond paying G1 when it matures at time 1. So, this is sort of a perverse special case with little n equal 1, and it collapses to a bond. But when little n is 2 or more, I mean, it looks very different. So here again is how we value the stoption, probabilistically speaking. And suppose little n, the number of periods, the maximum number of periods it's alive is 2. Then applying the crank, like you could exercise on day 1, in which case you exchange the first period price ratio for G1 and get G1, or you could instead exercise on day 2, in which case you would, by not exercising on day 1, get the first period price ratio S1 over S0, but instead of multiplying that by the second period price ratio S2 over S1, you multiply it by little G2, the second period floor, because you're exercising on day 2. So you want to value this, you have this choice of when to exercise. And so you're going to take the max of the 2 values at time 1, the stopping value G1 and the continuation value. And so we see that the valuation is the same as valuing a convertible bond. So a convertible bond, in case you're not familiar, is a bond that lets you keep it as a bond if you wish, and we're thinking the face value would be G1, or instead converting to stock and written into the convertible bond term sheet is the number of shares of stock you can get. And so if 1 share of stock is worth S1, then in this convertible bond, you're getting G2 over S0 shares. And so that's called the conversion ratio. So let's say, to get an actual formula for this payoff, which is a 2-period stoption and a single period convertible bond, we need a pricing model. And we'll start with Black-Scholes, but we'll actually switch to a different model later. So let's just sort of, write the payoff in the context of the Black-Scholes model, and then we'll actually value it in the Black-Scholes model. So we're interested in a 2-period stoption, which is the same as a 1-period convertible bond. And, I've been using 1 day as the length of the single period. Let's just call that delta t to be more general. So sigma is the instantaneous volatility in Black-Scholes model. And to get let's say, the volatility over 1 day, you would have to take the annualized volatility sigma and multiply by the square root of delta t. And the resulting number is dimensionless. So volatility has units, 1 over square root of years. And but when we multiply by the square root of something in years, we get a dimensionless quantity, and we'll call it little b. So, okay, now the gross return over the single period in the Black-Scholes model is S1 over S0, and that's log-normally distributed, and it has a mean of 1 under risk neutral measure, and it has a, a width parameter, which we're calling B. And so it's the dimensionless vol. And so LB stands for a log normal random variable with mean 1 and width parameter B. So this B is actually the standard deviation of the log of this log normal random variable. And okay, and anyway, the payoff of a convertible bond when it matures at the end of the single period of length delta t is the maximum of the face value G1 and the sort of value of the risky underlying, which is, from one perspective, you think of it as G2 over S0 shares, each worth S1. And from a different perspective, since LB is that gross return, you have to multiply the gross return by G2, okay, to describe the random component of the payoff. Okay, so there's that payoff again at the top of the next slide. And obviously to value it in the Black-Scholes model when we have 0 rates is to just take expectation of that payoff. And so that's what we have to do when, this highlighted quantity is log normal, mean 1, and width parameter B. So people are very familiar with Black-Scholes type calculations of vanilla options like this convertible bond. So this turns out to be the formula. And so capital N there is the standard normal CDF. And, the two positive numbers, G1, which is the face value, and G2, which is in the conversion ratio, and multiplies the price ratio and the payoff. Those two numbers are somehow combined to produce a third positive number. And so let's keep that in mind. So, so since we're combining two positive numbers to produce a third positive number, and we can say that there's a binary operation going on in the Blackburn-Scholes model to produce a convertible bond. And so this binary operation, we can wonder what properties it has. It turns out to be commutative, and it turns out to have a neutral element, which is 0. So if, for example, the face value was 0, then a convertible bond paying the larger face value in some number of shares is worth the number of shares. Okay, and so the algebraic structure we're working in to value the two-period stoption, or equivalently the single-period convertible bond, that algebraic structure is this one. So the set we're working on is non-negative reals. The binary operation is defined above, and its neutral element is 0. And so it's a commutative unital magma, it turns out. So the key, but let's say this funny binary operation we just defined above, it turns out it's not associative. Now it turns out that ordinary multiplication does distribute over this binary operation. So if you consider the algebraic structure with two binary operations, namely this Black-Scholes addition and ordinary garden variety multiplication, then ordinary multiplication does distribute over the first binary operation. And so it's a ringoid, first of all, and but there's additional properties. So this highlighted multiplication, for example, is associative, and you don't actually require associativity of the second binary operation to be a ringoid, but we have it. Okay, and moreover, there's a neutral element for that times in the set of non-negative reals. So, so anyway, so the second sort of part of the structure involving times, that's actually a group, whereas the first part is definitely not a group. It's not even a so-called semi-field, which to be a semi-field, it would require associativity. So the best you can say for the first part is it's commutative unital magma. Okay, so anyway, so we've been thinking about a two-period stoption, and we also previously thought about a one-period stoption. Next natural thing to think about is a three-period stoption. And so what are the payoffs of a three-period stoption? Well, you must exercise once. You could exercise at time 1 and get G1. You could exercise at time 2, and then if you did, you would get the first gross return times G2 because you're replacing the second gross return with G2. Or you could exercise at time 3, in which case you would get the product of the first two gross periods, gross returns times G3. So, you can do backward induction to value this 3-period stoption in the Black-Merton-Scholes model. And so if you do backward induction, you would sort of start at, say, time 2, then the value would actually just be like pretty much a bond value because you're forced to exercise at time 3. Then you step back a period to time 1, and then the value would be a convertible bond value, which is what's highlighted. And then you need to step back to time 0, and then you actually have a convertible bond whose underlying is a convertible bond. Okay, and so you would end up getting this calculation. And notice there's brackets in it, and you cannot drop those brackets because this binary operation is not associative. So anyway, we can just sort of consider an n-period stoption, use backward induction, and get a closed form formula for the value, and this is it. So, so this is a fairly interesting achievement. We've taken a garden variety model called Black-Scholes, and we've taken a very difficult payoff, from a stoption, so it's path dependent, has Bermudian optionality, and we value it in closed form. So, so that's pretty good. And but a natural question kind of arises is that, is there actually an arbitrage-free model, which won't be Black-Scholes, where we can drop the n-1 pairs of brackets that we're seeing in this expression? So the answer is going to be yes. And there's a distribution that is similar to log normal, but is not log normal, that we'll need to become familiar with. So the distribution is going to be called conjugate powered Dagom. I know you've never heard of this distribution. If you happen to have some expertise in wealth, in studies of equities of wealth, like wealth inequality in economics, the Dagom distribution is used there occasionally. But this conjugate power prefix is actually my terminology. Okay, so anyway, so let me just remind you that geometric Brownian motion is a continuous time process. And since the stoption involves Bermudian exercise, not American exercise, we can actually consider just a discrete time process instead of a continuous time process. And when we valued the n-period stoption of Black-Merton-Scholes model, we were basically using the embedded discrete time multiplicative random walk in it. So we're that's what we did. And now we're going to replace the log normal distribution describing price ratios with something that's both more realistic and more tractable. So I actually used to think that nothing could be more tractable than Black-Scholes, but I think I found something that's even more tractable. And so the price ratios are going to be IID just as they were in the Black-Scholes model, but the common law is not going to be log normal. It's going to be conjugate power Dagom, which is again a distribution you've never heard of, but I'll be happy to tell you what it is. So the price ratios will still have mean 1, and they'll still be fully described by a second parameter, which governs the width. And but let's say what's a little bit different is that this parameter governing the width takes values in the unit interval instead of being non-negative. Okay, so it's not literally a volatility, which is a non-negative number. It's a dispersion parameter, which is required to be inside 0, 1. So basically what's happening is that the tails will be heavier for this distribution than they are for the log normal. And so you can't scale you can't have a width parameter that's too big, like bigger than 1, or else you run into trouble with the heavy tails. So that's what's actually going on. And so we're going to use these risk-neutral discrete time dynamics to get an even simpler formula for the value of stoption. And this formula is going to just be the LP norm of the n guaranteed gross return. So if you know functional analysis, you know an LP norm is a measure of the, is a map from the n elements of a vector to the non-negative reals. And we'll be using that well-known map. So it'll be convenient to work not with the P in an LP norm, but its reciprocal. And the reciprocal will be this quantity B that describes the width. So if you wanted to probabilistically describe the P in an LP norm, it's a measure of the precision as opposed to the width. Okay, so so let's actually mathematically see what this Dagom distribution is and its conjugate power Dagom special case. So there's two people who sort of deserve credit for this particular distribution. Not surprisingly, one of them is named Dagom, but the other who actually did it much earlier is a guy named Burr. And so Burr actually proposed 12 different distributions, one of which was this one. And so, so anyhow, the easiest way to describe this Dagom random variable is via the cumulative distribution function, CDF. So the CDF is in the top bullet point here. And there's three parameters in the sort of general Dagom distribution. We're going to specialize down to two in a minute. But at the moment, there's three, and they're called mu, p, and q, and they're all positive. So the Dagom random variable is positive as well, and or non-negative actually. And okay, so the mu parameter controls the location, but it's not literally the mean. The power parameters P and Q control the shape, but neither is literally a width parameter. Okay, so we're going to specialize things. So we're going to require that one of these parameters, P, be greater than 1. And we're also going to require that the two parameters, P and Q, be conjugate to each other. So by conjugate, I mean this. And so we're going to reparameterize as well as specialize. And so we're going to introduce B as the reciprocal of P. So when the smoke clears, when you impose the restrictions and use B instead of P, you get this CDF for the conjugate power Dagom law. And now mu is the mean of this random variable D. And there's only one other parameter besides mu, and it's B. And B is a measure of the dispersion or width, but it's bounded. So we're using letter B as a reminder, it's bounded. And so if you wanted to go from the familiar notion of volatility sigma used in, say, the log normal distribution of Black-Scholes to the less familiar notion of width B, I provided a handy dandy conversion chart right here at the bottom. And you know, this is actually one of several ways to convert, but this is now my current favorite, so we'll just use this one. So so if we do use that approach, then we can compare the log normal distribution, the log normal density function, which is the dashed orange PDF, with the conjugate power Dagom, which is a solid blue PDF here. And some things you might be able to pick up is they're both unimodal. That one's easy. But moreover, there's heavier tails if you look at the wings of the conjugate power Dagom than log normal. And that's a good thing because whenever we apply Black-Scholes in practice, we find that practice typically has heavier tails than Black-Scholes will provide, which is why we often have smiles in options prices. Okay, so so there's a CDF for a standard Dagom random variable by standard. I'm making the mean be 1. So earlier we had a mean mu, now mu is 1. And you know, to describe a gross return under risk neutral law, we need a mean of 1. So okay, so we can use this alternative distribution instead of the log normal distribution of mean 1 to value a convertible bond with the same conversion ratio as we had before, which is also a 2-period stoption. So if we do the math, it just turns out that the formula is super simple. and is what's highlighted. So if you recall, the counterpart in Black-Scholes involved cumulative normals, and here I would say what's highlighted is much simpler. Does not involve any special functions like cumulative normal, and moreover is just an LP norm of the two vector G1, G2, where we've used the letter B instead of P, where B is 1 over P. Okay, so so this is why I'm saying that this model is even simpler than Black-Scholes, because I mean all we're doing is valuing a vanilla option here, a convertible bond. And so anyway, let's try and illustrate this approach. So say this parameter B that needs to be between 0 and 1, it's a half. Seems like a reasonable value to pick. And say that the first floor of this option is 3, and the second floor of this option is 4. Now those numbers are fairly high. If you recall, when I earlier illustrated this option, I used like 1.1, and that would be a much more typical value. So I'm choosing these high numbers just to sort of make the math easy, not to be realistic. And so let's say that just by coincidence, the stock price of the underlying is also the second floor, so 4. And so the conversion ratio of the convertible bond, it was G2 over S0, and I've made them both 4. So the conversion ratio becomes 1, which is a nice conversion ratio for our little example. So we have a convertible bond, and in this example, its face value is 3. It's got a unit conversion ratio. The current stock price is 4, but the stock price at maturity is random and is the highlighted quantity. But the highlighted quantity would have a risk-neutral mean of 4. So, okay, so before we impose this conjugate power Degen model, let's appreciate that as long as the underlying is non-negative, then the lower bound on the CB convertible bond value would be the intrinsic value, which is the max of 3 and 4, which is 4, and the upper bound would be the straight sum of the face value and the current stock price. Why? Because if instead of holding this convertible bond, you could hold both the bond paying 3 and the stock currently worth 4, it would cost you 7. And at maturity, if you liquidated that portfolio holding both assets, you would have the sum of the bond value of 3 and the random stock price. Whereas with the convertible bond, you're not getting the sum of 3 and the stock price. You're getting the larger. And what would you rather have? Two things, both positive value, or the larger of two things, both with positive value? Well, if you're greedy like me, you prefer both. So you'd rather have your cake and eat it too than just have one. And so the upper bound of convertible bond value is the straight sum, the cost of getting both. And so we know that the value in general to arbitrage free has to lie between 4 and 7. And we could use the Black-Scholes model value and get some value between 4 and 7. Or we can use this conjugate power Degen model value and get 5. So I can tell you that the Black-Scholes value would be less than 5 because it's got thinner tails than this conjugate power Degen model value. So sort of interestingly, we're combining the numbers 3 and 4, which are the two floors of this option, to produce the value 5. And if you recall, when I did the volatility example at the beginning of my talk, I combined volatilities of 0.4 and 0.3 to get a value of 0.5 for vol. So, same kind of calculation is being done here. And so we can go from this convertible bond value to a vanilla option value. So convertible bond is a bond plus a call, and it's also a put plus a stock from put call parity. So if we say subtract the stock price from the convertible bond value, we get a vanilla put. And having a vanilla put, we can calculate implied vol, do that for any strike in maturity, and we get this implied vol surface. So in the Black-Scholes model, this would be flat, and in this alternative model, because it's got heavier tails, you get a smile. Okay, so the point is that we have a binary operation being employed to value a 2-period option or 1-period convertible bond. And the form of the binary operations right here, I'm going to skip this middle bullet point and just point out that the form is like what's highlighted, that you're taking two numbers, little g1, little g2, and you're mapping them, okay, using a map G inverse to some other space where you're adding them and then mapping back with the inverse of the original map. So, we're actually, the map we're using is to raise to a power. So we're taking G1 and G2, raising them both to the same power 1 over B, ordinary adding them, and then doing the inverse operation of raising the power 1 over B, which is to raise the power of B. So, so the calculation of the 2-period stoption value, which captures optionality, that calculation is isomorphic to ordinary addition of the two floors. So isomorphic means structure preserving. It doesn't mean you get the same number. It means that you have all the same structure as ordinary addition. So what's happening is ordinary addition is being considered over positive reals. And that is, an ordinary addition is associative and has a, if it's non-negative reals, it has a neutral element, which is 0. And so we consider ordinary addition over non-negative reals. That algebraic structure is commutative monoid. So basically, it's not a group because it's lacking the existence of an inverse in the set of non-negative reals. So if I take the number 3 and I ask, is there some non-negative real I can add the 3 to get 0? The answer is no. So anyway, so we've got a commutative monoid in when we do ordinary addition of non-negative reals. And we have the same thing, a commutative monoid, when we value using the conjugate power Dagom model. And the key thing is that this conjugate power Dagom inspired binary operation is associative. Okay. So so I'm kind of going to skip some of this blah 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 because it's just trying to connect the finance to the terminology in abstract algebra. Most of you are finance people, I suspect, so not so interested in that connection. So anyway, we're valuing a 2-period adoption by this LP norm calculation, and it is a binary operation. So we can just define a binary operation. This is circle plus B. The B there is the width parameter in the conjugate power Dagom model. So for every numerical value of B between 0 and 1, there's a binary operation we're defining. And so we really have a family of binary operations when you consider the totality of the little b's. And okay, so you can ask, what properties does this binary operation have? And I think I've already told you. So it's commutative, associative, has a neutral element, which is 0. Okay, and moreover, ordinary multiplication distributes over it. So, so it's basically kind of in some ways, a generalization of ordinary addition. If I actually let little b be 1, which, let's say, I didn't allow when I wrote it that way, but if we did like little b equal 1, it just is ordinary addition. And so, we're basically kind of extending ordinary addition by introducing values of b strictly below 1, but still above 0. And, keeping all the algebraic structure that ordinary addition has. And moreover, giving a financial interpretation to that extended addition as, let's say 2-period stoption valuation in this conjugate power Dagom model. So, okay, so these properties we're going to allow us to easily value n-period stoptions. And and it's going to be easy because we have an associative binary operation. And so, we have to do, let's say, convertible bond on a convertible bond, that's a compound option, which normally is quite difficult. But because of the particular model we're working with and the particular payoff, things are going to be pretty straightforward. So, okay, so the model is going to assume the price ratios are independently identically distributed, conjugate power Dagom law, where the price ratios have unit mean. And you just have to do dynamic programming. And I see that if I only have like 5 minutes left, so I think I'm going to spare you the algebra that is needed to do the dynamic programming. But let's say, all I want to say is that we use the algebraic properties that we have to come up with this explicit formula. And I'll just say that it's a little bit easier than in Black-Scholes because we have associativity. So a 3-period stoption, for example, or sorry, a 3-period stoption would actually be valued this way, but we're actually evaluating an n-period stoption with 3 periods to go. And so let's say there's this prefactor. And so when we sort of dynamic program our way back all the way to time 0, we end up with this valuation formula right here. So the key thing is, let's say, is it's similar to what we had previously with the Blackburn-Scholes model, but the big difference is we drop the brackets. So so it's, you know, a repeated pseudo-sum, and you're not so familiar with that circle plus b, but so fortunately we can rewrite it using, you know, an operation that you've seen before called ordinary addition, and this is the formula. So it's just an LP norm, and so, you know, so that's what happens, and you get a nice simple formula. So it's a Bermudian option, and so you might want to know when should you exercise early, and we have an explicit strategy, which I don't have time to go through, but basically there's these critical gross returns that you can just calculate explicitly in closed form, and if the gross return is below that, you exercise early. Okay, and finally, you know, so I only talked about pricing. What about replication, which is also hedging if you were to sell one of these? And it turns out you can replicate, and you have to use 1-day options to replicate an n-based option. If it was an n-month option, you use 1-month options. Okay, anyway, and you actually do a rolling over strategy of these short period, single period vanilla options. And let's say the fact that there's a nice simple replicating strategy is also due to the algebraic structure, especially associativity. So, okay, so let's actually illustrate with a 3-period stoption. I'm going to use numbers that are, you know, just sort of make the math easy as opposed to being realistic. So the first floor will be 12, and the second floor will be 4, and the third floor will be 3. And so we have a 3-period stoption. There's this width parameter b that has to be between 0 and 1 for the conjugate power Dagom model. We'll make it a half again. And so we need, you know, according to the formula, we need to combine, you know, 12, 4, and 3. And we actually saw for a 2-period stoption that, you know, the value when the floors are 4 and 3 is 5. And so we can just take that 5 and combine it with 12, and we get 13. So you might recall 5, 12, and 13 is a Pythagorean triple. So we're using that fact. And, you know, so as I mentioned, you know, the optimal exercise strategy is just simple explicit formulas. And for this 3-day stoption, the critical gross return is 12/5. And so if you get a gross return below that, you should exercise in the first day. And moreover, there's a replicating portfolio. It holds $12 in bonds. That $12 is 12. And it also has $1 in 1-day calls. And the strike is just of the 1-day calls is just the current stock price times 12/5. Okay, so so the, you know, the floors were 12, 4, and 3, but actually, if it had been, for example, 3, 4, and 12, or 4, 3, and 12, or any of the permutations, you would still get the same value of 13. So, that's specific to, the particular Bermudian contract and the particular model, which is conjugate power Dagon law. Okay, so, in general with early exercise, order matters, but let's say there can be counterexamples. And all right, I think I'll skip, this, but it basically says, isn't it cool that actual derivatives always involve the max, because algebraically speaking, everything distributes over the max that's increasing. And so just here's a quick summary because I'm out of time. So we propose an approach that values optionality between two attractive alternatives. And we just thought of it as a binary operation combining the two values. So for example, the two floors of the two periods option. And we first illustrated with the Blackburn-Scholes model. And there the binary operation is commutative and has a neutral element, but is not associative. So in order to get an associative binary operation, we switched to the conjugate power Dagon model. Our new associative binary operation is isomorphic to addition, which is also associative. And the generator that allows us to go from ordinary addition to this new binary operation we use to value a two periods option or more is the generator is power function. So ordinary multiplication distributes over our new binary operation. It also distributed over the Blackburn-Scholes one. But when you're demanding distributivity of ordinary multiplication over an associative binary operation, then the distribution we identified, conjugate power Dagon, is actually the only one that works. Okay, so the statement is, if you're working over the set of non-negative reals and you're kind of demanding that ordinary multiplication distributed over the optionality binary operation, and you demand that optionality binary operation be associative, then the corresponding laws are the one we used. But if you relax associativity, you could use law normal. Okay, and the associativity though is useful because it leads to replication. So I'll just say that I happen to be working with underlyings that are non-negative, which is very common in finance. But, we thought crude oil futures were non-negative until one went negative last year. And so it can be useful to think about other sets besides non-negative reals. So you could, for example, work over the entire real line, which let's say for crude oil futures, people are now doing. You could also go the other way and have like a smaller set. So say prices that reside in the unit interval. That's not as restrictive as it sounds. So, so for example, I have an argument that VIX is to be thought of as a bounded random variable in the future, not an unbounded random variable in the future. And so if VIX is, say, in the future bounded above by, say, 400%, I can always just say that means in terms of its largest value, it's between 0 times its largest value and 1 times its largest value. And so I'm actually writing a paper where VIX is bounded and as a fraction of its maximum value lies in 0, 1. And and as we saw with like velocities for Einstein, consider it as a fraction of the speed of light, they lie in -1, 1. And so there's all kinds of different sets you can do this work in, but we'll save that for another day. So anyway, if you want more details, then I have a paper on my website and also on SSRN that has more details. And in that paper, I actually considered the security prices to be real as opposed to non-negative. And so anyway, if you use the camera on your phone and snap this QR code, you'll be taken to my website where the paper resides. So that's it. Let me stop sharing. And I see there's some stuff in chat. So yeah. Okay, so Cleopatra in chat said, they can guarantee a 10% markup in China's stock market at least. Okay. Um, so I guess you're referring to the stoption value, because it would be such a great thing to have, because I know you get crashes just like we do in the US. And then there's something in Mandarin, which unfortunately I cannot read. Rickson, do you know what that's saying? Oh, okay.
Right, yeah, that's not quite related. So,
Okay.
so first of all, yeah, thanks, Professor Carr, for the very elegant talk. And it's really eye-opening to see how abstract algebra can be applied to option pricing. And I think we can maybe take one or two quick questions if the audience still has them. So if anyone has questions, feel free to unmute yourself. Or maybe in the meantime, I can start with one quick question. Oh, I think we have a question.
Yeah, hey, Peter, thanks for the great talk. It is Juba here. I have two questions. The first one is, so at some point in the slides, you have a bunch of these operations stacked together, and the structure really reminded me of a neural network. And, we talked about using this
right.
kind of,
that's a fantastic observation. Yeah.
So yeah, just could you make a comment on like how these kind of approach can be used in neural networks in general? And then the second question is, so I was wondering if this approach is useful for sort of all sorts of path dependent options. For instance, if you have a barrier type of feature, how do you incorporate that?
Okay. So on the first point about neural networks, I agree. Actually, as you know, activation functions are used in neural networks, and ReLU is a very common one, which is is the max, okay, zero and a quantity. And so a different activation function that's also used is called soft plus, and so there's a real valued counterpart to everything I presented today, and that's actually the paper that QR code takes you to. And so the soft plus activation function is actually the two-period stoption valuation function when the underlyings are real. They're the same thing. And so basically, like you can say that when we're valuing the stoption, we're doing a neural net with n layers, but we're skipping the optimization stage that is part of a neural network when you do optimizations to determine the weights. Okay, so there's definitely a close link between neural nets and this valuation, and I could potentially change the definition of the stoption to incorporate the optimization part that's missing, or the least squares part that's missing. Okay, and then make it truly a neural network. Okay, on the second point about barriers, so that is connected to my last slide where I said you can work with different domains. So if you if in particular you had bounded domains like 0, 1, or -1, 1, you can think of the reason for the bound as being the knockout barrier, and so that would be yet another way to extend the stoption payoff to incorporate barriers as well. Like although when we think of barrier options, like we typically think in continuous time and then monitor continuously. And so far, let's say I was presenting a discrete time approach. It actually does turn out that in many models that are commonly used in practice, you can convert monitoring continuously over time into monitoring once, with changing the payoff to incorporate the difference. So that's basically what the reflection principle is about. Okay, so So I'm, optimistic that one could incorporate continuously monitored barriers as well in this contract. And so that's a nice suggestion, which I hadn't actually thought of until now. And so, so I'll think about it. Okay.
Thank you so much.
All right. Yeah, it's actually already very late over there in New York. So that in the interest of time, let's probably stop here. Thanks. Let's thank again for Professor Carr's
Recording
excellent
stopped.
talk. Thank you very much.